Hello, everyone. My name is Xiangyi. I work in the chain signatures team. So this talk will mostly about the technical perspective, like why we wanted to build it, how it works in the backend, and what you can build with it. So to start, I want to talk about the motivation, like why we wanted to do it. So I want you to imagine that you are a developer at Sweatcoin. So Sweatcoin is a big D-app on Near that has millions of users. Let's just imagine you work for that kind of app. And then what you want to do right now is you want to onboard all those users onto some other D-app on other chains. So for example, Farcaster on Base, right? So how would you actually try to do it? OK, so this is me trying to do it. So I think first step is I will try to create an account for the user on Base. And obviously, I need to worry about the private keys, right? Like whether I should keep it or I should ask users to keep it. And the next thing is I want to figure out where the gas comes from for Base, right? So when we think about gas, then there involves another creation of account on ETH, and then there's swaps, there's bridging. So we all know that there is a lot of trouble involved. Like when we think about creating accounts, where does the private key go, right? If the user loses their private key, everything is kind of burned to ashes. And then the second thing is when we go through the swaps and bridging, your assets can be stuck, your assets can be delayed, a lot of things can happen. So when you're a developer and you're trying to make that happen in the background, a lot of things can just go south. So that whole thing is kind of why we wanted to build chain signatures. So with chain signature, it can just be as simple as that. You just know that your user has a Near account. And the next thing you know is that that user has some address on each of the chains that they can interact with. So for example, in this case, your Sweat user will have a derived address on Base, and then they can just directly start using Farcaster. And the key magic behind making that happen is actually this. So with chain signature, one Near account can control one address on each of the chains. So this is like twofold. The first fold is there is a unique mapping between the Near account and the address you get on each of the chains. And the second fold is this Near account is actually able to control all these addresses without actually having access to the private key of those addresses. And this talk will mostly focus on how we make that happen. So before we go into the technical details, I want to talk about the high-level architecture. It's actually pretty simple. It's just two things. So first is a chain signature smart contract. The next is a set of nodes that are supporting the contract. So the way you or any developer interact with this system is just by calling the contract. And the most important function in this whole thing is the sign function. So as you can see, what goes into it is a payload, which is typically the transaction payload that you want to do on other chains. And then the path, which is the derivation path. Typically, it kind of signals which chain you're going for, and then a key version, which is something built inside of us. So this is how you're going to interact with the system. And at a high level, what's going to happen is whenever you do this sign call, the set of nodes that are supporting the contract, as we see in this slide, will coordinate with each other, and then they will generate the signature and then return it back to you. So now you might be wondering, OK, why is this system about this sign function? Why is this sign function important? So I think that's like the key question we want to answer, and I will try to do it in this talk. But before we go there, I want to introduce a central concept of this whole system, which is the root key. So this root key is kind of at the center of making everything happen. So it's at the center of how we derive all these addresses from Near accounts, and it's also at the center of how we enable the Near account to actually control these addresses. So I want to start with how this key is generated. So when we first initialize the smart contract, what happens is this set of nodes that are supporting the contract, they will coordinate with each other and kind of go into a computation protocol. What they end up with is each of the node will have a private key share located locally on the node. And the next thing they do is we will kind of assemble these root private key shares into a root public key, and we will expose it in a contract, so which means that you can see it just by calling a private key function on a chain signature contract. So one thing I want to point out is you can see in this whole picture that there is no private key anywhere. We are not trying to assemble the root private key share into the root private key. That's for essential security reasons, and I will get to that later. Okay, now I have talked about where did we get the root key. And now I want to talk about why is it important? Like, how is it important in deriving the addresses for the near account? So the key thing here is actually when we try to derive the address for each of the near account, we are actually calling this derived key function. And as you can see, what goes into it is the public key, which will be the root public key of the chain signature system, and the epsilon, which is derived by a predecessor ID, which is basically the near account that's calling the contract, and the derivation path, which is a string. So we further summarize in this slide, which is like when we try to derive these addresses on other chains, what we take is the root public key of the chain signature system, the near account, and the path. So that is why chain signature needs to be involved in this derivation so that your derivation of the address is unique and deterministic. And basically, if you're not doing that through the chain signature system or you're not using the chain signature root key for this derivation, your derived address will be different and it's going to be wrong. Okay, so that is how we get this unique mapping between near account and addresses on other chains. And the next question we want to explain is, okay, we know that these users, they can derive these addresses, but then how do they actually use these addresses? Because they don't have the keys, right? So before we go into the detail there, I want you to imagine that you create your own account on, let's say, base, right? So if you did create your own account, what's going to happen? It's that you're going to be given a set seed phrase, and then you're going to be given a private key. And when you are trying to do any kind of interaction with any kind of dApps on the base chain, what happens is you use that private key to authorize all the transactions, which is basically that you're trying to sign all the transactions with your private key. So now we come into the case where this address is derived. And remember, previously we said that the way we derive these addresses by this derived key function, and what goes into it is the root public key and your near account, and then we get a unique address. And then we take a closer look at this code. We see that there is this derived secret key function that go hand in hand with the derived key function. So what goes into this derived secret key function is actually the root private key of the system. So if we actually get the root private key in there, we can get the private key of the derived address. So this is very important because it established the link between this derived address and between the root key and the root private key. And this kind of explains why this root private key can sign for users. So this summarizes exactly what we talked about. If we have the root private key and the near account, theoretically, we can derive the secret key. However, as I have mentioned, we are not assembling the private key from the private key shares. We only have the private key shares. So this path of directly deriving the secret key in order to authorize transactions is just not going to work. So how are we going to actually control these addresses, right? There is no private key. So when we think about that problem, we further take a step back and think about what's the most important thing when we say, I have ownership of this base account. So when I say I have ownership of this base account, what I mean is I can actually do all the transactions. I can decide whether I want to say yes or no to a transaction, right? So the key here is not whether you have the private key. The key here is you are able to sign all the transactions. So what if, although we don't directly have access to the private key of that derived address, we can still somehow sign it. So this is exactly what chain signature is able to do. What it does is it uses the root private key shares, and it's somehow able to sign for all the transactions on behalf of the derived addresses. And I would explain kind of high level how we use these private key shares to generate a signature in the next slide. So let's now, we have talked about that the architecture of the system is smart contract and a set of nodes that are supporting it. So let's say there are 3 nodes in the system. So each of the node will have one root private key share. So whenever a sign function call comes into the system, it will also come in with the near account that's calling it, which is the account here, and also the path. So what will happen on these backend nodes is each of them, together with their private key share value, will go into a protocol. And then what I mean by a protocol is basically they will do some computation locally and then kind of exchange that value with one another and do some further computation using those values and like a couple of rounds and back and forth. And then when they got some value out of that protocol, they further compute with the account they got from the sign request and the path. And now what they get is a derived presignature. The reason why I call it derived signature is it is corresponding to the derived address that this user is targeting. So it's unique to the near account and the path that's calling it. So basically, if the near account that's calling this sign function is different, it's going to be a different derived presignature. So now each of the node has a derived presignature for this sign request. The next step is each of them will take the payload of the transaction, and then they will generate a signature share on each of the node. And the last step of combining everything together is that we will combine all these signature shares, and then it will form a complete signature for this transaction. Okay, so now we have explained how chain signature was able to have this unique mapping between near account and derived addresses, and also how near account was able to sign transaction on behalf of these accounts. So now we want to put it together. So how does this one near account actually do something on base, right? So it's as simple as 2 steps. So the first step is with your near account, you call the sign function on the chain signature contract with the transaction payload that you wish to sign on other chains. It can be base, it can be anything else. And the second step is you combine that transaction with the signature, which comes into a signed transaction, and you send it to base and completes your transaction. Okay, so that kind of wraps up the high-level explanation of technically how we make a near account able to sign transaction on other chains and control other accounts on other chains. But I also want to spend a couple of minutes talking about why our system is secure. So I think the key thing I want to point out is with chain signature, if you're developing on it, you don't have to worry about your user's keys. So as I've mentioned, if we don't have chain signature, if you, as the Sweat developer, if you want to onboard your user onto any other DApp on other chains, what you need to do is you need to create accounts for them, and then you need to safekeep their keys. But with chain signature, you don't even have to worry about that. There is no way anyone can just steal the user's keys because, as we have mentioned, the user's keys are derived basically from the root key. And since I've mentioned that our root private key is never assembled anywhere, we only have the private key shares. So there's no way for anyone to say, okay, I'll just steal the user's keys, or even I'll just steal the root private key. It's not available anywhere in our system. And furthermore, we also keep it more secure by kind of keeping the root private key share values hidden. So as I have mentioned previously, in this kind of protocol, right, we see that the root private key share values actually does need to enter into some kind of protocol. But even in those cases, the nodes, they will never exchange the root private key shares directly with one another. Whenever they want to send any kind of value to each other, that value must be a computed value of the root private key share. So that computed key value, you can think of it as some kind of function applied over the private key share value. And that function would always be an irreversible function. So when I say irreversible, I mean it's kind of like a hash function where if you have the input, it's very easy to get the output. But if you have the output, it's kind of impossible for you to deduce what goes into it. So this is how we are able to hide the root private key shares from the network and from one node and another. The last thing I want to mention about our system is we can actually guarantee a very high uptime. The reason why we can do it is we are employing this T out of N signing. So when I say T out of N, the example is like, for example, on our production mainnet, we now have 8 nodes that's talking with the contract. So on mainnet, we are using 5 out of 8 signing, which means at any time, as long as there are 5 nodes that are alive online, we can still respond to the sign requests. So this means that our system can tolerate up to 3 nodes being offline, and then if anyone tries to attack the system and take it down, they need to at least take down 4 nodes, which becomes kind of at least non-trivial. Okay, that's all I want to talk about our architecture. And I also want to spend the last few minutes talking about what people are building on us. So there are smaller projects and there are bigger projects. I want to start with smaller projects. I think this one coming from KeyPalm called multi-chain trial accounts is especially interesting. The use case they're trying to target is, imagine that you're building a D app, and then you want to give each user $10 to try things out on your app. But what user typically ends up doing is they just rug the account, right? They take the money out and they're not using your app in any way. So what multi-chain trial accounts try to do is they will whitelist the allowed actions on all these kind of D apps, and then if the user was trying to do something else, they will just directly ban it. And the way KeyPalm was using chain signature was that with chain signature, they are able to list all the D apps of all the chains in one smart contract, and then they're able to use chain signature to do the cross-chain stuff. So I think that's a very interesting case because it's a small one. It's not like 100 people building for 2 years, but it's super useful, and it's a very good example of replacing the heavy lifting with chain signatures. So I think that's a very good place where people can start and thinking about what use cases there are. And on to the bigger projects, we have Diffuse, which is like a marketplace where people can trade keys with assets, and the Infinex, which is a secure non-custodial cross-chain wallet. It came from King, who is the co-founder of Synthetex, and also Sweat Wallet, who's trying to onboard their users onto DApps on other chains. Okay, so much for the talk. This is our QR code for the developer channel, and you can also add me, and then these are some examples to follow. Thank you.